Okay, let's get started. So, if you remember, last week we saw the future of the universe, right? We saw that based on the current cosmological parameters that Anson also showed, dark energy is, well, how many percent? 68%, right? And according to dark energy, our universe keep expanding, and then we lose sight of all the other galaxies except the local universe. So that's our sad future of the universe. That's what we saw that. And today we're going to go into a new chapter about cosmic microwave background. Cosmic microwave, have you heard the phrase that says cosmic microwave background is the holy grail of the cosmology? You know, holy grail? Have you seen Indiana Jones? No? No. Harrison Ford is looking for this kind of holy grail? No? You guys are too young. But I think Harrison Ford has a new movie, right? New movie, so maybe you, when you watch the new movie, Indiana Jones, Indiana Jones. So you learn about that. But in case of cosmology, CMB is still holy grail. From CMB, I think when you learn that, you will be surprised so many things you can learn about universe from cosmic microwave background, including the value of cosmological parameters and also flatness problem. So that's why so many people are interested in cosmic microwave background. It's just a light, it's the remnant of the Big Bang. When the universe was small and then big fireball, it was high temperature, right? And it expanded and it's low temperature. And now it becomes a low temperature, and so it emits in microwave, and then it comes to the Earth from all the directions. But it's just a cold wave, but we can learn so many things. That's what we're going to see now. Okay, let's get started. And then today we're gonna see the 3 evidences of the Big Bang. Okay, this is going to be in a test. Okay, so this you should remember. Okay, at the end of the class, I'm going to ask you what are the 3 evidences of the Big Bang, right? So, don't worry, I'll explain. Expansion of the universe, and then cosmic microwave background, and then primordial nucleosynthesis. This is also very interesting. Okay, let's get started. So, maybe you know this story. In 1964, you're taking notes? Excellent. Okay. In 1964, Arnold Penzias and Robert Wilson was doing an experiment, building this radio antenna. And this was partly for telecommunication and then partly for observing the universe in radio. And when they built this very big antenna, they noticed there's a noise coming from in all kind of directions. You put the telescope this direction, that direction, there's always noise. And then they try to figure out what are these, okay? But they couldn't figure out. They thought it may be a noise from New York City, and then they put the antenna away from the New York City. There's still noise. There are some, birds living inside. Then, they clean up the bird's poop. They call it they call it white electrolytic stuff or something like that. But they, clean it up, but it's still there. So they didn't know what this noise is. And then they're trying to publish a paper about unknown noise of the universe. Or they didn't even know it's a universe. They may be from detector or whatever. And then they hired this Robert Dick. He's a professor at Princeton. Heard about this paper. They are trying to publish a paper. And then this Robert Dick immediately understood they detected the cosmic microwave background. And then he said, oh boy, we're scooped. Because Robert Dick, he's a theorist. And he was actually trying to do the similar, he actually, theoretically understood there may be cosmic microwave background, and he was actually himself was trying to build this kind of antenna to detect the cosmic microwave background, and at that time he heard the news of Penzias and Wilson. And so Robert Dick called Arnold and then Robert Wilson, Penzias and Wilson, and then told them, okay, you guys detected cosmic microwave background for the first time. And then later, they published a paper. So Penzias and Wilson published the observational paper about detecting cosmic microwave background. And then Robert Dick wrote a paper about theoretical interpretation of this detection. And then, as you may know, that in 1978, Penzias and Wilson got the Nobel Prize on detecting the cosmic microwave background. Okay, then, so this is 1964, they published this paper. But back in history, theoretical prediction was already in 1948. This George Gamow was already theoretically predicted there will be a cosmic microwave background. Well, this is the famous alpha, beta, gamma paper. So George Gamow was created this Big Bang theory model, right? Which we're gonna look at it later, maybe later today or next week. Then he predicted there's such a microwave light because from the big one, fireball big one, and the expansion of the universe, temperature cool down, and there will be a microwave radiation from cooled remnant of the Big Bang, hot fireball. So that is, this paper was, and then George Gamow wanted to write a paper about this, and then his student was Ralph, right? And then he wrote a paper with the student, and then Ralph is alpha, right? And then Gamow is G, gamma, right? So he's missing beta, alpha and then beta. So he called his friend Berman. He did nothing to the paper, but his name is Berman, right? So it's B, right? So they wrote the paper together, three guys, and then that's completed alpha, beta, gamma theory. So that's a Big Bang paper. Very unique personality. So, good. And then maybe I should go. Yeah, then predicted temperature is 2.7 Kelvin. So that's very cold, right? It's in terms of Celsius, it's minus 270 or something like that, right? So that's very cold. That's why it's in microwave now. And very interestingly, there's a paper in 1934 that is even before George Gamow, from this Andrew McKellar, and he published a paper that the effective temperature of the interstellar gas, the gas in the universe, is 2.3 K. So what he did is he observed some molecular clouds. Who is doing star formation? Are you doing? You got this star formation? If you observe molecular cloud, you sometimes get emission lines, right? And then from molecular vibration or molecular emission, whatever. And then those emission lines from molecules, they have different excitation temperature. So by comparing the line ratio, you can measure the temperature of the gas. How many degrees is this temperature? What they did is this, and they measure the temperature of this gas as 2.3 Kelvin. That is very close to this number of the cosmic microwave background, right? In fact, what they measured is the temperature of the cosmic microwave background, because cosmic microwave background is in principle, it's a minimum temperature of the universe, because the universe is filled with a cosmic microwave background. So anything lower temperature than that is heated by the cosmic microwave background to this temperature, right? So this gas was heated to this temperature. And of course, the measurement in 1934 is not so accurate, so there's a little bit difference, but this was the temperature of the measured temperature of the cosmic microwave background in 1934. If they wrote a paper, but then it's unfortunate, they wrote a paper saying effective temperature of the gas. If you wrote a paper that say, okay, we detected the cosmic microwave background, maybe they are the one who received the Nobel Prize, but at that time no one knew about it. Okay, so that's a discovery story of the cosmic microwave background. Maybe we can look at the picture. So this is a picture of the cosmic microwave background. Maybe you should look at this. It's very uniform. It's 2.7 Kelvin, and then it's coming from anywhere. So in this color scale, this is a 4-degree scale. It's all uniform. See, 2.725 Kelvin plus minus 0.001 Kelvin. It's very big difference from Anson's Hubble parameter, right? It's super accurate, it's 0.1% accuracy from any direction. This is, in fact, this is the most perfect black body radiation in the universe. We people, human, cannot create such a perfect black body in a laboratory. And then, well, if you lower the color resolution, you go to color bar to 3.5 millikelvin, still millikelvin. Then you see the Doppler motion of the Earth. The Earth is moving, right? Our solar system is moving around the Milky Way galaxy. So the direction that we are facing, we see the blue shift, and then direction behind the radio wave is going to redshift. So we see a dipole. But this is just because of the motion of the Earth. So we subtract this dipole motion, and then you go down to 18 microkelvin level, then you start seeing fluctuation. Do you know what is this?
Milky Way?
Yes, Milky Way, that's right. And then, this is a COBE satellite, which also received Nobel Prize. COBE satellite map. And then this is the WMAP, NASA's more later satellites, higher resolution. And if you go to microkelvin level, you start seeing a little bit of fluctuation. And this is your father and mother. Okay. I will explain what I mean, but then you are born from this fluctuation. You are the son and daughters of this fluctuation. So next time you see this picture, you should say, oh, mother. Oh, father. Okay, this is true. This is true. So one of my friends is in a WMAP team. Okay, and then when they observed this, they did a press release. Okay, from the news reporters and TV crews, right? They reported like, okay, NASA made a new satellites and observed this, and they showed this image to reporters, right? On the next day, on the newspaper, this image was on the newspaper, right? And then they said, oh, here's a very beautiful cosmic microwave background here. No! Right. This is Milky Way, right? But TV reporters, they are not scientists. So. And then my friend learned. So from next time, since then, every time he make a press release to the news reporter, he photoshopped this and hide it. Otherwise, okay. Anyway. So that's the figure, and then next, next we're going to look at why. So I said cosmic microwave background is a perfect black body radiation, the most perfect in the world. But why is it such a perfect black body radiation? So we're gonna see a little bit of that, and then what I want you to learn is this: actual temperature of cosmic microwave background scales with 1 plus z. Okay, so let's see that a little bit. Here, so this is a spectrum of a cosmic microwave background. This is Colby's observational result. And then this is plotting the intensity of the radio wave as a function of frequency. And then this black curve is just this Planck equation, Planck's black body radiation equation. And then those are data points, right? And the data points perfectly agree with the Planck equation, this, right? This Planck equation. That describes black body radiation. And then what we're going to do, what happens? But the universe is expanding, right? So that's how this temperature gets lower, lower, lower from the Big Bang fireball, and lower temperature, lower temperature, lower temperature. How did it happen? Is this when the universe expands, there's a redshift. So the frequency of the cosmic micro background is going to be shifted as well, redshifted, right? The frequency is going to be 1 plus z longer, right? So that's how frequency changes. It's like an ambulance thing, right? Then let's put this in. So the new frequency when the universe expands to some z is this. So we put this in a Planck equation. And the Planck equation's nu is here, right? Here. So you put, instead of nu, you put a nu times 1 plus z. And then this nu 1 plus z to the cubic, right? And then you do this, the converters, and then it becomes again write it down in this kind of equation. And then what you find is this form, redshifted form. So this is redshift form from that. From that, if the universe expands, this becomes this. And if you look at it, this is again Planck's formula, right? This nu and EH nu and dV and T. And then what's different from that one? The difference from this original Planck equation, where's my mouse? Do you see my mouse?
Yes.
How come I don't see it? Anyway, what's different from here is that, so this is the same shape, right? I forgot 3 here. I need 3 here.
Yeah.
But then, except that it's the same shape. The only difference is this T. This T part now becomes T divided 1 plus Z. So that's the only difference. So if you consider, so that means this part, green part, is a new temperature, right? If you count this as a T dash, and then it's the Planck formula, right? And then that's how, maybe I shouldn't use this. Then it'll be okay. Yeah, so here. So that's, then if you write new temperature, T dash is going to be here. So it's T divided 1 plus Z. So that's going to be new temperature. So with the expansion of the universe, the temperature is going to be like this. So T emitted divided T observation is going to be 1 plus Z. So that means when the universe was, when a higher redshift, that means more in the past, the temperature was higher, right? Now it's at 2.7 Kelvin, but the temperature was higher, right? So it was the temperature of the CMB was warmer in the past. So can we check? We can check actually. So at redshift 2.7, okay, maybe I can ask. Where should we go? Ashwin is here today? Not here. Alex is not here. Okay. Then Poya. So what's the temperature at redshift 1? CMB temperature at redshift 1. So the this temperature scale 1 plus Z, right? And the current temperature is 2.7 Kelvin, right? So what's the temperature at redshift 1? Okay. Did you say 5.4?
Yes.
Yes, right. So this at redshift 1, this is 1, right? So 1 plus 1, 2, right? So twice higher, right? So 2.7 times 2, it's 5.4, right? So 5.1 degree. And then someone did the experiments. They measured the temperature at redshift 2.4. And then they measured the temperature of 9 degrees. This is it, observation. But theoretically, if you put 2.4, then temperature is 9.2, so that's really close, right? So that's the minimum temperature of the universe. So if someone tells you that, oh, at redshift 10, I found a gas, and then its temperature was 3 degrees. Does it make sense? It doesn't, right? Minimum temperature of the universe at redshift 10 is like 30 degrees. So you cannot find a 3-degree gas in that high universe because temperature of the universe is 30 degrees. So everything is heated up to 30 degrees. So if you see a paper saying temperature of the gas at redshift 10 is 3 degrees, you should say, oh, this paper is wrong. Okay, then, okay, the next, Lucy, what's the temperature of the universe at redshift 10? Let's do 1,000. So the Big Bang happened, was around redshift 1,000. So what's the temperature at the time of the fireball? 1,000. Oh, should I make it 999? It's easier for you to calculate, right? You can look at this.
Yeah. Can you repeat the question?
Okay. What's the temperature of the cosmic microwave background at redshift of 999? Yes.
Yeah, it will be 1,000 times.
So the current temperature is 2.7. So 1,000 times 2.7.
27. 2700.
Yeah, 2,700. Right? So that's the temperature of fireball at the redshift 1,000. Okay. Then you might wonder if it's like 3,000 degrees, there might be nuclear synthesis, right? That's what that's what this alpha beta gamma paper discusses. Okay. Okay, now we ask a next question. So now, okay, we learned how the temperature changes as a function of redshift, right? Next, we ask a question, why CME is such a perfect black body? So I said, it's a very perfect black body single temperature. Why? It can be in one part of the universe it's colder and then another part of the universe is hotter. Why this doesn't happen? Why it's such a uniform temperature? That's what we're going to see next. For example, then to answer this question, why CME is a perfect black body, we can rephrase this question as this. Was there enough time for the universe to mix? Okay, so imagine a bathtub here, okay? And then you put, open a cold water and hot water, right? And imagine you put hot water here and cold water here. Now, at the beginning, the temperature is not uniform, right? It's hot here, it's cold here. But if you have enough time, after a very long time, temperature is going to be uniform, right? And mixed, right? So the question here is, did the universe have enough time for mix to hot temperature, hot temperature? If it does, then it can be a single temperature. If it doesn't, the temperature may not be uniform. And to do that, we need we need to compare the two time scales. The expansion time scale. So if the universe expands faster than mixing time scale, then it's not uniform. If the universe expands or mixing time scale is shorter than the expansion time scale of the universe, the universe is going to mix and then become black body, right? So let's compare this. And then first is the expansion time scale. Expansion time scale is this dynamical time scale, scaled something like this: G gravitational constant and low density of the universe to the inverse square. This, if you take a stellar dynamics class, then you learn it like this, okay, in a very high density dynamics. And then in this radiation dominated universe, we didn't do that in detail in the last or 2 weeks ago, but then here in the very early universe, the universe is dominated by the radiation because temperature is 3000 degrees, such high temperature, it's fireball. So the radiation is dominating the universe. What I mean is energy in the radiation is much larger than the matter or dark energy or whatever. Just the radiation, high temperature, because the whole temperature is 3000 degrees. Then in such a universe, density scaled with scale factor to the -4. The reason you might wonder, this is why this is not 3. Because 3 you understand, right? It's the 3 dimension, the space is 3 dimension, and then scale factor is the length. So if the volume becomes, if the scale becomes twice larger, volume becomes 8 times larger. So it's 3, right? That's for normal materials. But for the light, there's another dimension, it's wavelength. So when the universe expands, light wavelength also becomes longer, right? And then it loses energy there. So that's why it's 4. So the 4 is 3 dimension plus wavelength 1 dimension. That's why 4. Okay? And then you put this here, okay? Density, the density of the radiation here, and then because this is square root, it becomes 2 plus 2, right? So dynamical time scale of the universe is proportional to scale factor to the square, okay? Okay. That's one point, okay? And then now, the thermalization. So the mixing time scale. Thermalization time scale is the time scale of interaction between, photons hit each other, When you make friends, when new students make a friend, become friends, you first, punch each other, right? And they hit collisions, and that makes peace, right? So that's the same thing. Okay, then collision is not true. Maybe it's not true. Okay, but then here collision makes the temperature mixing, right? And then collision rate is, of course, students' number density to the square, right? Because this is two-body problem. 2 students hit each other, right? So student density times student density makes the rate, decides the rate, right? And then number density. In case of student doesn't lose energy on the wavelength, so it's just R minus 3 dimension, right? It's square because it's 2 students. So this is -6. Okay. So the collision rate in the early universe. Now we're talking about photons, not students. Okay. Say hot photon, cold photon hit each other, mixing. Then it's scaled with R scale factor -6. Okay.
I think it's bions, it's not photon.
Eh?
If
What's
it's
the
a
question?
photon, then it should be partial to power raised to -4.
No, this is just the number density of photons, not considering energy. Previous one we are considering energy density, but this is hit collision or not, so it's just the number density, even for photons. Good question. Actually, that's a good question. The summary. Okay, to summarize what I discussed here. Summarize, when scale factor is smaller, so that's in the early smaller universe, then when this R becomes small R universe, the collision rate increases with R to the -6, right? And then dynamical time scale is R to the -2. Here, R becomes smaller. So both of these increases in the early universe, right? Smaller, if the universe is smaller, collision rate is larger, right? Okay. And now I have a question to the next person. Who's next? Liz is not here. Then Jishen. Okay. Then which one is going to be larger when R is smaller? Okay, be careful. When R is getting smaller in the early universe, because the universe is getting small, which one is going to be larger? Collision rate or dynamical time scale? Okay, let me ask a question. 6 and 2, which is large? Yes, that's right. So smart. NTH students are so smart. So in the early, when the R is very small, more collision happens than a dynamical time scale, right? The collision is very high, a lot of collisions. So that means there's enough time for mixing. Because the universe was very small. Okay? So that's why the universe is uniform temperature here. So the answer to this, why CMB is such a perfect black body, is because the universe was small. When the universe was small, there was enough time for mixing hot part and then cold parts. That's why such a perfect black body. And then, as you can see, this is to the -6 versus to the -2, right? So the universe is smaller. This difference is huge. Right, order is different, order different, so that's why. Okay, and then so this is actually the supporting evidence that we observed that in observation we observed a very uniform temperature of the cosmic microwave background, right? Here we observed cosmic microwave background very uniform, 2.7 plus minus 0.001 Kelvin. It's very uniform. This is supportive evidence of the hot Big Bang model of the alpha beta gamma theory, because at this time there are another theory that called steady state universe. This is not expanding. Universe is not expanding. Then those theory try to explain cosmic microwave background maybe from dust in the universe, because dust, low temperature dust, can also emit. If it's 3 Kelvin, it can emit microwave, right? However, this steady state universe model cannot explain uniform temperature of the universe, because if there's a dust here, their temperature can be different, right? It doesn't have to be uniform temperature. So this uniform temperature is one of the evidence of the Big Bang theory that universe was smaller and uniform temperature. That's why now CMB temperature is uniform. Okay, we can look at again. See, this is again comparing the. So this is comparing this light. This line is the 2.725 Kelvin black body radiation. This is not a fit to the data. And then these Kobe's data points with error bars 400 times larger. And then as you can see, this follows a perfect black body. So that's the most perfect black body human ever seen in the universe. Okay, so that's okay. Then maybe